All right, so a little bit of logistical talk before we get into the slides and memory examples is uh, the lecture learning objective 1 checkpoint is upon us. That is today. So I don't have a specific time on this. You may have noticed it's just vaguely Friday. So I want to clarify what this means. I've said this before, but it was like day one. It feels like an eternity ago. I'm sure most of you don't remember what I said. I don't even remember what I said, or at least how I worded it. But this is the learning objective 1 checkpoint, which means after Friday, once it's no longer Friday, so you can think of this, if you just want to think of this as a midnight deadline, an 11:59 p.m. deadline, knock yourself out. That's a consistent way to think about it. But once it's not Friday anymore, it's fair game for me to start doing my LO1 checkpoint processing. So I'm going to look at your second chance lab and interview, get those all processed, look at your pale blue dot, look at what you have there, and process everything together. And if you have your learning objective complete, all three parts of it complete, there's nothing to do. I just say, great job, you're doing fantastic, keep up the good work. And if you've missed any of those, that's where it's recovery plan territory. So if you're missing any one of those three, then I'm going to come up with a recovery plan and send you a plan of how you can make up the parts that you are missing, whatever they may be. Those plans, you can expect them at the latest by Tuesday. So I will have, which means I'll have all the interviews, myself and the TAs will have all the interviews graded, the labs graded, the results back to you for the second chance ones. Your homework process, which you have the auto grader, so the only time you're worried about that is if you didn't complete all the auto grade stuff. All that will be processed by Tuesday is my deadline. I won't go to bed on Tuesday without having that complete. So it might be technically 2 a.m. on Wednesday, but I won't go to bed until then. If you don't have it by Wednesday's class, you can get really mad at me. For the application objective. So wait, before that, the learning objective. So the question I've gotten a few times is, should I keep working on the lecture objectives for Pale Blue Dot as we approach this checkpoint? The answer is absolutely yes. If you haven't completed it yet, like, you have to complete that. If you have any questions about that, go back to the syllabus and understand how the grading works for this course. But you have to complete that. You have to complete LO1 right in order to pass the class. So even if it's Friday night and you haven't gotten it done, you wake up Saturday, you're like, man, if I just had a little more time, keep working on it. That's why the auto lab deadline, the auto lab assignment for this, will let you keep submitting for another 24 hours. And then after I get the recovery plans out, I'll update this. This is me saying by the end of Saturday, I'm going to have the actual deadline up, or at least just change it to Sunday if I'm falling behind, or Tuesday. But you can still keep submitting after the kind of due date. I have a due date just because Autolab makes me have a due date. So you can still work on those because you have to finish those to pass the class. You have to in some way show me that you can write code applying the LO1 concepts. So don't stop working if you're working on the learning objectives. Because at a minimum, your recovery plan is going to include a deadline extension and what you need to accomplish to be able to satisfy the right portion of that. And that'll be out to you by Tuesday. So keep working on those. The application objective is a little more questionable. That will be more of a deadline here. You won't be able to work on the application objectives after I do the checkpoint review. So it's up to you. This one's a little more risky. I will definitely wait until after Friday, so at least midnight. But once I pull submissions, once I download all the submissions and start processing everything, whatever I have as your submission when I pull them off Autolab, and I'll pull them all at the same time so it's fair for everybody. If you're the last one to be graded, you don't get an extension on the deadline, an effective extension. So once I pull the submissions, then whatever you have at that point is what your application objective is. So you can roll the dice and hope that I pull them at noon tomorrow or whatever. I might, if I'm awake and working at midnight tonight, I might pull them right at midnight. So it's up to you what you want to do. But whenever I pull them, if you want to take your chances or not. Quick reminder that you don't need all the application objectives to get an A. So if you miss this one, it's not that big of a deal. Just go on to the next one. Just get the next ones. Okay. Are the application objectives extra credit? That's one of those questions somebody can take a shot for. Just read the syllabus. You should know what an application objective is if you're looking at the grading structure. So let's get into some slides. Anybody watching on YouTube, that reference isn't going to make sense, but there may or may not be a drinking game going on in chat. It's acceptable. We're all in college. We're all adults. But don't drink if you're under 21. I feel obligated to say that. So let's get into some slides. Encouraging shots. Oh, yeah, and it is 2 in the afternoon where I am, but I don't know where you are. It might be after 5 p.m. where you are. Who knows? It might be 10 p.m. If you're over 21, enjoy a shot. If it's 10 p.m. where you are, have a shot and a lecture. I shouldn't say that during the YouTube portion, but what's done is done. All right, let's talk about this memory example, and we got a good example for today. I'm really happy with this example. Hopefully, you all agree. Hopefully, it makes sense, and these concepts start getting hammered down. No strictly new concepts today. We're just reinforcing things from Monday and Wednesday. Monday and Wednesday's lectures contained a lot of stuff, a lot of brand new stuff that's going to take a while to understand, and I am aware that that's going to take a while. So this is kind of what I call a digestion lecture. We're just reinforcing all the concepts with a more complicated example. So if you didn't understand Monday and Wednesday, don't sweat. Don't sweat too much. We're going to reinforce those topics today. That said, the lecture task is the same one. This is the same one from Wednesday. No new lecture task today. Because after just Wednesday's lecture, I don't really expect that, unless you're really studying on your own quite a bit, I wouldn't really expect you to be able to do those one just after Wednesday's lecture. It's going to take today's lecture to really understand how to do this, and specifically how to do the testing and how to fail that no OOB% solution on Autolab, that incorrect solution. How to write tests that's going to fail that one. So if you weren't able to do this on Wednesday, no problem. That's why this is a 2-lecture task. And as far as not understanding the stuff, there are times where I can slow down a bit, but also on the other side of that, Monday's a new topic. Monday is inheritance. Wednesday is another new topic, polymorphism. Friday's another new topic, state pattern, which are all pretty related. It's all kind of one topic, but it's going to be a little bit before there's another digestion lecture. It's actually the following Monday. So 3 more lectures of learning stuff, and then another digestion lecture, and then a whole week of digestion lectures, actually. So let's take a look at this example. I'll let you stare at the code for a little bit. I'll give a quick overview of what this is, but we're actually only going through one example today. It's this example, and we're going to look at this example in depth. We're going to look at every single thing that's going to happen during the execution of this program. So one thing off the bat, I needed to save a little bit of space on the slide. So I didn't add the class definition or the object definition here, but you can assume that win battle and main are in the same object. And in fact, they are. If you go to the repo, this whole example is in the repo. These are in the same object. So when we call win battle right here, it is seeing this win battle method right here. So this is a very simple simulation of a little bit of RPG mechanics. We're going to have players, player characters, and they're going to be in a party that's going to go adventure around the landscape, fighting monsters and gaining experience, and also tracking the number of battles that they've won. So a character in this game is going to know how many battles it's won and how many experience points it has. And also, if that character is part of a party, how many battles that party as a unit, how many battles that party won, and also the experience points and battles won for each member. So if a party wins a battle, the party remembers that. Each character remembers that they won a battle, and each character gains experience points for that battle. And we're not dividing the XP, for those of you who've played RPGs like this. We're not dividing the XP. Everybody gets the full XP for what it's worth. mostly just so I can avoid integer division. But and I don't want to work with doubles for this example. No, we don't actually have any import statements for this program either, because these classes are all in the same package. When there are classes in the same package, you don't have to import. If they're in different packages, we would have to import. So I'm actually not even excluding any import statements, but I am excluding the package statements at the top that say package lo2op dot memory dot RPG example, whatever I named it, something similar to that. You can find it in the repo. So I am excluding that, just so I can fit everything on the slide. Because we are going to fill up this slide. This is one of the few lectures where I take advantage of the widescreen slides and I start using the margins. I'm going to use this whole thing. If you don't believe it, just get ready. It's going to be exciting. Can you override variables in modifier class? Sure. You just have to be careful about names. Actually, I can't answer that. We haven't even gotten to that yet in lecture content. So I'm not going to answer things like that during lecture. I shouldn't even read that one. So let's go through this thing. Who's ready? Who's ready for this? So we're going to start our program at the start of main. That's where no, it's not your fault. I just, that's one of the things I shouldn't have responded to. After lecture, I'll be happy to talk about it. So we start at the beginning of main. That's where we always start our programs. And once we start, oh yeah, a few of you are ready. Once we start the program, we're going to get stack space. We're going to say, hey, operating system, I'm about to start a new program. Give me some stack space. I need some stack space to store all my stuff. So we get our stack space like we've learned last week, and that you've been interviewed about up to 2 times. You've taken quizzes on this. You should be pretty solid on the stack by now. And that is going to come back. We're going to see how the stack and the heap interact with each other in this example. And we're going to bring back stack frames. It's going to be a lot going on here. So we start the stack and we put our command line arguments, which again, we don't use in this class. And we create a stack frame for the main method. I excluded here's the start of the main stack frame in here. But this is where it would be in the main stack frame. And we put those command line arguments in that stack frame. The next 2 lines, we should be really comfortable with these. I'm going to explain a little bit more just to reinforce something, is that mob XP and boss XP, we're going to put both of those on the stack with the values that they are assigned to. And since these are ints, this is one of our types that I call a primitive type, because they'll be compiled down to primitive types when they're in Java bytecode. These types are going to go on the stack directly. So this is an int. We have int, double, long, char, boolean, byte. Does Scala have a byte? I don't think it does. I feel like I'm forgetting 1 or 2, but those types are all going to go directly on the stack. So the value 20 and the value 100 go directly on the stack. We don't talk about heap for ints for these values. They go directly on the stack. Everything else goes on the heap, including a party character. So we're going to create a new object of type party character, which means we're going to call the constructor of this class. This class has a constructor that takes no parameters. And then once we call the constructor, we're going to execute all the code that's outside of the constructor, and any variables and values that are declared are outside of the constructor. Outside of any of the methods, we don't happen to have any methods in this class, but all the code outside of the methods is executed, and any variables or values that are declared in that area, in that, it's got to have a good name. I call it the initialization area. I don't know if that's what it's supposed to be called or not. Are going to be part of the state of that object. So the state of the object is any constructor parameters and any variables that are declared outside of all of the methods. So this object, when we ask the operating system, we say, hey, we're creating a new object of type party character. We're going to need some space here, operating system. We're going to need some memory to store this thing. It's a party character type which means it's not going on the stack because it's not an int, it's not a long, it's not a double, it's not a char, it's not a Boolean. We're going to have to put this on the heap, so we need more space for that. So we need enough space for 2 ints and whatever overhead we have for the party character class. Operating system says, here you go, here is your memory space, and it's going to give us a chunk of memory enough for our overhead and our 2 ints, and it's going to give us a reference to that spot in memory. So the operating system says, yeah, I got your memory for you. It's at 428, some reference that lets us find that space in memory. Now, I didn't mention this enough Wednesday. Let me mention it here. These numbers, I'm completely making them up. They have no inherent meaning. The 428 has no inherent meaning. It's just some number I made up. When I was writing these slides, I'm like, what memory address should this be? I don't know, 428. There's no thought that went into those. When you have your quiz for this learning objective, you can do the same thing. Pick whatever you want for these references. I see a lot of students just using @1, @2, @3 for their objects. It's perfectly fine as long as you're consistent. This reference, this number here, has to match this reference here. What that number is, it doesn't matter. And if you run your program multiple times, you'll get different numbers each time. There's a lot of meaning behind that, but that's for the JVM and the operating system to care about. We don't have to care about that. So we asked the operating system for memory. It gives us enough memory for our object and 2 ints. It says it's at 428. We go to this memory address at 428, and we say, all right, we need a variable named battles1. So let me use up some of this space creating an int named battles1 with a value 0. Let me create an int named experience points with value 0. And since the operating system is going to give us exactly as much space as we need, we're going to fill up the entire space for that section of the heap. That's not a mistake that this filled up the whole thing and the stack has empty lines. The stack, we get more space than we need, so we have kind of like a scratch paper as we're working. The heap, we're going to get exactly the amount of memory that we need for that object. So we get that. New is going to return the reference. New is going to return the reference. So new returns this at 428, which says how we can find this object again. So we went somewhere on our RAM stick. We don't know where. We're saying it's this kind of nebulous at 428 here. And new is going to return that reference, and that is what's stored in the hero variable. So we often say, and I'll continue saying this throughout the semester, that hero is a variable of type party character, which is a little bit misleading. Hero is actually a variable of type reference to party character. Hero, the variable, only stores the reference to that object. It only stores the reference, and then we can use that reference to find the object on the heap and access its state and behavior and modify its state if we need to. So hero stores that reference at 428. And then we can move on to this next line. Now we're going to see a method that takes a party character and an int is the way I would say it. But this actually takes a reference to a party character and the value of an int. So we got a few things going on with this method call. We're going to call win battle. The stack frame for main is going to remember that it's right here waiting for this method to resolve. But that's it's out of scope right now. It's not accessible on the stack frame right now, but it is paused. The execution is paused, waiting for this stack frame to finish up its thing and return. So main can pick up right here and continue along its program, along its code. So we create a new stack frame because we have a method call. This method creates 2 parameters on the stack, character and XP. So we need to resolve the 2 arguments to values so we can assign them to the parameters. Can we not declare party character as a type? So whenever we create a new class, Oh, like the keyword type, like type party character? I'm not actually familiar with the difference between type and class, if that's even a thing. I might have made that up. But whenever we say class party character, we're creating a new class. That's the same as creating a new type. We have a new type, which we can have variables of this type, hero of type party character. And we take a parameter character of type party character. When we wrote that class, we created a brand new type. So we need to resolve the arguments to values. For this, it's fairly simple. These are stack lookups. These are resolved before the stack frame hits the stack. So these variables are in scope, and we look up the values. Hero has value 428. So this resolves to 428. 428 is assigned to this new variable character of type party class, or reference to a party class, and character gets the value at 428. It does not make a copy of the object. This is not getting a copy of this object. It is getting a reference of where we can find that object in the heap. So where in memory can character find an object of type party character? At 428. That's the only information that's passed into this method. And then mobXP, we look this up on the stack. MobXP has the value 20. So that value 20 is assigned to this XP variable. Since that int is storing the value directly on the stack, the value 20 is passed to the method, not a reference to an int that has the value 20. It's strictly the value 20. So this is a copy of that int. Since this is one of those primitive types, this mobXP, this XP gets a copy of the value stored in mobXP. This is technically true. I mentioned this on Wednesday too. This is technically true for references as well. The character is getting a copy of the value stored at hero, but that value happens to be a reference. So technically we're passing a value. This is still passed by value, but the value is a reference. For our purposes in this course, I will refer to this as pass by reference. It's a little bit inaccurate, but for our purposes here, I'm gonna be okay with that. In 220, you will have to know the difference between pass by reference and pass a value by reference and pass by value. You will talk about all those in the differences between all three. For our purposes, we'll confuse pass by value and the values of reference with pass by reference. So if in your interview in 2 weeks, your interviewee or TA says, explain pass by reference to me, that's what we're referring to. And if you really know what you're talking about, you can be like, well, technically, Scala doesn't pass by reference; it's passed by value, and the value is a reference, and then you'll get, you'll pass that interview with ease. Yeah, don't only say that. Clip that. Well, I said the thing he said in lecture. I passed, right? Well, no, because you just memorized it and you don't know what you're saying. If you know what you're saying and you understand that and you can explain it, you're definitely getting past that interview. So anyway, so we get these parameters on the stack inside the stack frame. Yeah, you got to explain it in your own words. And then we're going to execute the code of this method. So for this, we're using the dot operator, which is going to take a reference and access the object that is being referred to. So when I say character dot, I'm saying character, I know you're a reference, and I don't give a crap about references. I don't want the reference itself. This means nothing to us. It's just instructions of how to navigate your RAM stick. I just don't care. I don't want the reference. What I'm interested in is the object that's being referred to. And that's what the dot operator gives us. This says, character, take me to the object that you're referring to, follow these instructions, and take me to that spot on my RAM where this object is. So we're saying character, which is at 428 dot, follow that reference, and take me to this space in memory. So after the dot operator, we're over here. We're no longer on the stack. We're over on the heap. And now we're accessing the battles1 variable. The battles1 variable in this spot on the heap is right here. And we're going to increment that from 0 to 1. Same thing with experience points. We're going to access that object on the heap, and its experience points variable, we're going to increment that by 20. This 20 is the value in XP here. Reference. I won't say reference as many times this lecture as I did Wednesday. Wednesday I was introducing the concept, so I said it, just talking about it, I had to say it a ton. Today's a good mix of heap, stack, reference, object, stack frame. You're going to get a good variety on this one. Is it already 16 though? Jeez. Maybe I am saying it a lot. We reached the end of the method call. Stack frame's destroyed. Character and XP are gone. But we still have a reference to that object at 428. And in that method call, that method had code that followed a reference into heap space and made changes in heap space. Since those changes were made over in heap space and we still have a reference to the object that was altered, we can see those changes. This method happened to return unit. So its stack frame is gone, its parameters are gone, its local variables are gone. The stack frame is gone. But those changes persist because those changes were made in the heap, not on the stack. All the stack stuff is gone. The stack doesn't remember that method call, but the heap does. The heap always remembers. So the heap remembers that those values changed. And now if we did hero.battles1, we're going to get 1 here after this call and 0 before this call because that object changed. Is everyone cool with that so far? Because this next line is a lot going on. So since this method, this hero, this party character hero, that was passed by reference, and whenever we pass a reference to a method, we have to be aware of this, that when we get that back, or not even when we get that back, but after this method call, that method might have changed the state of that object that's being referred to. So it's something we always have to be aware of. Whenever we're giving a method a reference to one of our objects on the heap, that method can change that object's state. Something to always be cautious about. That can happen, or that you're doing that. Sometimes in most cases in these courses, you're going to be the culprit. You're going to call a method, and that method, you're going to change the state of your object, and then you just break everything throughout your code. It's something you need to be aware of. So let's move on to this next line, and we're going to fill up this slide here. We're going to make use of all this space. So a lot just happened there. Let's break this down and talk about what's going on in this line where there's quite a bit going on. Not too much. Yeah, don't be scared, Johan and Lanthorns and Lucas. Don't be frightened. But we do got to talk about this a lot. So I'm going to set on the slide for quite a while until you all get this. And ask questions as we go. Make sure you understand what's going on here. Because this is pretty much the crux of things. If you understand this line, and I'd say the next line, then you're really good. Then the last two are kind of cool down period. So we need to create a new party. But to do that, just like in math, we have to evaluate what's inside the parentheses first. So before we create a new party, we have to resolve both of these constructor arguments to values so we can assign them, so we can evaluate the outside the parentheses and create this new party and assign those parameters. So first, hero. This one we just did on the previous line, so we should have this. We're going to look at our stack, look up hero, and we see that that has value at 428. It's a reference to a party character, and we're good with that. It resolves to at 428. Done. The next one, new party character, we're actually going to call the constructor to create a brand new party character, but unlike hero, we're not going to store it in a variable in the main stack frame. This variable never gets this value never gets a variable in the main stack frame. So we're going to create a new party character, call the constructor, ask the operating system for exactly enough space to store our 2 ints plus overhead, initialize those 2 ints to 0, and now we have 2 objects of the same type, both in heap space, but at different references. So I use this class to create multiple objects, which is why we want classes. And those objects are in different locations. They each have their own copy of battles won and experience points that can have different values. We went to this space spot in the heap with our other method call and updated these values. When we create another new party character, we get a brand new space in heap. We get new memory addresses assigned to us from the OS. And we're going to have separate copies of battles won and experience points, which are initialized to 0. Now I made up some other number. Whenever when I whacked my keyboard to come up with this number, I happen to hit 272. So at 272 is going to be the location of this party character, this second character that we're creating on the heap. Now, since this resolved to 428, this resolved to at 272, we have our two values for our arguments, and now we can finally call the party constructor. So we're going to say, hey, operating system, I need some space. I need enough space to store 2 references, an int, and any overhead that the party class is going to come with. So the operating system says, yep, here you go. Here's your space for your 2 references and an int. Visually on the slide, it's 4 lines instead of 3, but the operating system is going to give us exactly how much space we need, depending on how much space we ask for, which the JVM and Scala is going to do that for us, do all those calculations. So we have 2 references that we need to store, character 1 and character 2 from our constructor. Character 1 is assigned 428. Character 2 is assigned 272. One of those came from a variable on the stack. One of those came from a brand new object that was created. New returns that reference. We could either store that reference in a variable, or we can give that reference directly to a constructor call. However we do it, that new returns a reference, and that reference moves around our code. Here we're storing that reference in this object of type party, and then running all of the code outside all of the methods, and any variables that are declared are going to go along with that object. So we create battles 1, initialize it to 0. Battles 1 is going to be attached as part of the state of this object in the stack. In the heap. I was looking at Sobi saying I was explaining this well, and I'm like, oh, good. And then I say stack instead of heap. Yay. But battles 1, we get that extra variable there, and that's going to be initialized to 0. So all the code outside of the methods is executed. Any variables that are declared in that space are going along as part of the state, are going to be part of the state of that object on the heap. New, again, returns a reference. This reference is to a party object. We're going to create a party variable on the stack and assign it the reference that we get from the return of the constructor call. And again, we created another new type, party. We can use this anywhere where we use our other types. Just anywhere like we used an int. We can do the same thing with our parties. We can do the same thing with our party characters. It's another type. It just happens to be a type that we made ourselves. So now this returns the reference at 596, another number I just made up. And that's going to be stored on the stack. Party refers to the object at 596. If we go follow that reference, we'll find an object of type party with these variables and values. If we follow these references, we'll find these 2 characters on the heap. Is there any way to access the second party character since it wasn't declared with a name? Yes, there is. And that's part of the rest of this example. So I will get to it. Let me make sure. 224. Yeah, I will get to it, but just to foreshadow, since you asked, party. When we do party dot, we're going to follow this reference, and then we're going to do dot character 2 to get this reference here. So we can access it, but we have to access it through this party reference. So party, follow the reference, get character 2 at 227. We can get that reference to that second character that was created. So we can't access it directly because we never stored that reference in a variable on the stack, but we can access it through the party object to get that value. And we'll do that right here, actually. This character2.battles1. Actually, that's the next thing I want to talk about anyway. Any other questions on this line and creating those two objects? We created an object inside a constructor call. And references are moving all around our code. And for anyone doing the reference drinking game, reference. Have fun with that. Well, if you didn't have new for the val party, if I didn't have this keyword new right here, I would get a compiler error. Yeah, don't actually do the shots. I hope. At least do this drinking game with beer. Can you go over it again real quick? This line? Yeah. So I'm creating a new party. Before I create that, I have to resolve the arguments. Hero, I look up on the stack, and I find it right here. New party character, I have to call this constructor. Ask the operating system for new heap space. Create this, because these didn't exist before this line. Ask the operating system for new heap space for party character. Create its variables, initialize that. So I have my arguments, new party, create variables character1, character2, battles1 after asking the operating system for another chunk of heap space. And we get 3 different objects on the heap at this point, all in different locations. We don't care where they are on the heap. All we care about is that we have these references so we know where to find them in the heap. The heap, where they are at exactly, that's up to the operating system to care about. We don't care about that. But we do know that we have the references to be able to find them. So now we have this party, which has 2 references to the other 2 objects and a battles1 variable. And then we assign that to the party variable, which gets the reference of where the operating system gave us the space to store this party object. If you don't declare if you don't have val right here, that'll be an error. It'll say party doesn't exist. Also, you're defining the type. What are you doing? That wouldn't work. If you didn't have new, that would also be an error. That wouldn't work. We would have to create what we call a companion object, an object of type party, and then define its apply method. We're not going to mess around with that, though. You got enough to worry about as it is. I'm not going to throw companion objects at you. So let's move on to this next line, because we got a doozy of a method call. So we're going to call a method. Here we're using the dot operator, and this is actually our first true method call. Yeah, everything's a method, and this is attached to an object, but this is our first method call of a method attached to an object that was created through one of our classes. So it's the first time we really get to talk about this. So party dot, we're saying party is a reference. I want to access the object that is being referred to. So party dot says head over to at 596. Head over there in heap space and access its win battle method with the argument boss XP. So we're over here at 596. We see, hey, this is an object of type party. To find this win battle method, we better go over to the party class and look for a method named win battle, which of course we find, because I wouldn't give you code that doesn't compile. And we have a parameter XP, which is boss XP, which is 100. Create a stack frame for the method call, assign XP 100. And we also have a kind of hidden parameter. And this is the difference between a function and a method, for those of you who are asking that. We have this hidden parameter of this, which is accessed through the keyword this, which stores a reference to the calling object. So whatever object called this method, which in this case is party dot, that's how we got to this method. Party was at 596, referring to this object. So this is going to store the reference at 596. This always stores a reference to the calling object. Yeah, exactly, repetition. So we don't, in functions won't have this. When we talk about functions, those are those functions are not attached to objects, so you don't have anything in this. This doesn't really exist. In Scala it does technically, but this is a reference to the calling object. Methods have objects that they're attached to, so objects are always going to have this with a reference to that object that called that method. So we have this on the stack, and we have XP on the stack, and let's start using them. So the first thing we do in this method, in this stack frame, is take this and access the object that it is referring to. So this has a reference at 596. So we head over there in the heap. We say, oh, at 596, we have a party object. It has character 1, character 2, battles 1. I want to access battles 1 at this point. So I'm going to access battles 1. And this value, which was 0 before this line, we're going to increment that by 1 through this line. We're going to add 1 to it and reassign it to itself. So battles 1 now has the value 1 at this object on the heap. Now we can also chain these together. We can, I thought I added another, did I mix up the order? I thought I added a, oh yeah, I see. This arrow is supposed to be right here. That's what I messed up. The arrow is supposed to be right here. So for these two lines, let's execute these two lines. For this, we're going to follow multiple references. So we have this dot. So this reference, we're going to follow that reference to the heap and see where it takes us. It takes us right here to this party. It has character 1, character 2, battles 1. We're going to access its character 1 variable, which stores a reference. So we're going to do character 1. So we're right here. Dot, meaning, hey, that's a reference, and I want to follow the reference. So at 428, I want to follow that over to the party character object, and then access its battles 1 variable and increment it by 1. So I'm going here, going to battles 1, and incrementing that value by 1. So this was 1 from our first initial win battle call, and we're pretty far deep. We went through a constructor call, through a method call, through accessing 2 layers of references, but we're actually modifying the same battles 1 variable that we incremented way back here when we called win battle, because that's how the references shook out. And that's the level you should be at when you're, it's a big game of telephone, exactly. And this is where you should be at for like your quiz in 2 weeks for solving the lecture tasks for these past 2 lectures, is being able to trace through all that and notice that this battles 1 is the same as this battles 1 in this program, because win battle was called with hero, which is at 428. So this was at 428 when it was called, and party was created with hero at 428. Win battle was called through that party, through that party object. That party object accessed that value from the constructor, which is a reference, and followed it all the way to the same battles 1 on the heap. This is just a toy example. How do you know if a battle is won or lost? We just assume that battles are always won. So we win every single battle. These characters can't lose. They don't have HP or anything like our other example too. They just always win, and they always gain the XP. Never lose. Why would we even program losing? Why would they even code losing into the game? That's just silly, right? Everybody wants to win. So then we do the same thing for the next 2 lines. We're going to follow this reference. We're going to follow character 1 reference. We're going to follow read experience points and increment. We're going to follow this to character 2 to experience points. And for battles 1, I didn't go over that one. Also, this, follow that, character 2 at 227, experience points, battles 1, increment them both. Stack frame ends. All that stuff's off the stack. Those references are no longer on the stack, but all those changes, all that stuff that was changed, it's still here on the heap. All those changes are still reflected in the heap. And this is what we call side effects. Whenever you hear that term, this method has side effects. That's what we mean, is that it made changes in the heap. Side effects. And let's do our 2 cooldown methods. We're going to call win battle a few more times. We're going to call win battle with party.character1. So this, we're going to follow party at 596, access its character 1 at 428. So this resolves to at 428. And mob XP 20. So it's going to be at 428 and 20. And that's what gets into this stack frame. So this stack frame's parameters, character and XP, 428, at 428 and 20. It's very similar to our win battle call over here, except to get character 1, we accessed the party object on the heap and got its reference to character 1. So when this method call happens, this is actually the same as the previous time that we had this method call, because last time we called this with hero. Hero stores a reference at 428. Party.character1 is party.character1 is also at 428. They are referring to the same object. They're different variables, but they're referring to the same object on the heap. So we actually go through the same functionality. Once we're inside this stack frame is identical to the previous stack frame when we called win battle, because it has the same parameters. We go over to the hero, we increment, we return, stack frame's gone, changes can be seen outside of that stack frame. Now we call this again, and this is how we access. So we never, this character here, this party character, we never store this in a variable directly, but we can still access it through the party class. So if we do party does have a reference to that object that was created. And if we do party dot, follow its reference to this object, and then do dot character 2, we can access that reference to that character. So we can still access this. We can still use this character. We just can't access it directly. We have to go through the party class to be able to access that. So party.character2, this stack frame of win battle is going to have at 272. This party character, which we can think of as character 2 in this example. Character 2, and then access its battles 1 and experience points at 272 dot at 272 character is at 272 dot battles 1, follow 272 to the heap, find a party character, access its battles 1 and experience points, and increment both of those values. Stack frame's destroyed and then gone. But notice we do get, at one point, we do get this at 272 on the stack. Even though it's not on the stack in the main frame, we can have it on the stack, and we could even say val character 2 equals party.character 2 and get that character on the stack in the main frame. We can do all that stuff. Frame ends, method returns unit, but it has side effects. We hit the end of our program. All memory is freed up. Stack and heap, it's all gone. Our poor little program has to get executed. And the memory's freed up. Oh, I didn't even switch that over. You know what? I'll just call lecture there. Any quick questions that should be in the YouTube video? Calling hero. So hero and party.character1. Hero and party.character1 both have the same reference, so they are identical. If you said if hero equal party.character1, that's going to return true because they're the same reference. If you compare references using equal, it checks if it's the same exact reference. Do these references refer to the same object? And there's ways to override that behavior, which is a topic for, I believe, Monday. It's definitely next week, but I think we talk about that right from Monday.